This is lesson 4.4. In this lesson, we're going to start talking about scatter plots. So if we look here, it says a scatter plot is a graph that shows the relationship between two data sets. The two data sets are graphed as ordered pairs in a coordinate plane. Scatter plots can show trends in the data. So we're going to look at this scatter plot over here, and we're going to answer a couple of questions about it. So this part up here gives us some information about the graph. It says the scatter plot shows the amounts X in grams of sugar and the numbers Y of calories in 10 smoothies. So they give us 10 different data points in this one. For part A, it says how many calories are in the smoothie that contains 56 grams of sugar. So if I want to look for the amount of calories for a 56-gram sugar smoothie, I have to look over here and notice how these are kind of counted, it looks like by fours. So in between each number, like halfway between would be the 2 mark, right? So it goes 54 to 58. So halfway between there would be 56. So if I go up on here, up to 56, looks like I hit that dot right there. So this dot here, if I travel over to that y-axis, it looks like 270 calories for that 56 grams of sugar. So 270 calories. For part B, it asks how many grams of sugar are in the smoothie that contains 320 calories. So this time I'm looking at my calorie side and I'm going 320 and I kind of travel over until I hit, oh, here's a data point right here. And then I have to travel down this line to see where it would land. And it looks like it lands at 70 grams of sugar. So then for part C, it says what tends to happen to the number of calories as the number of grams of sugar increases. So basically you're looking for look at the graph and see kind of what the data shows us, right? So as the calories, let's see, what's the calories as the grams increase? So sugar, as it's increasing, as we're going this direction, it looks like each data point kind of goes up as I'm traveling to the right. Now, is it a perfectly straight line? No, but it does look like this data tends, those points are going in an upwards direction. So if we were to write a result for that, then we would say as number of grams of sugar increase, I'm just gonna abbreviate number with the hashtag symbol. So as number of grams of sugar increases, number of calories increases. All right, so for the next section, we're going to talk about correlation. So correlation is a relationship between the data sets. And so if you look at a scatter plot, we can use those to kind of describe that correlation with the data. So if I'm looking at this right here, again, we always read our graphs from left to right, remember? So as I read this from left to right, it looks like this data is kind of making a pattern kind of in a straight line in an upwards direction. So that's why we would call this a positive linear correlation. If I look at the one next to it, it still looks like it's making kind of a straight line pattern. But again, reading from left to right, it looks like it's going in a downward pattern. So we would call this a negative correlation. Think about slope, like we talked about before. So my slope as I go from left to right, this is a positive slope. This is a negative slope. So it makes sense that the correlation would also be positive or negative based on those same trends. If I look over here, see how the data is just kind of like, it looks like they threw a bunch of dots on this graph. So there's no real pattern that we're seeing here. So for this one, we would say that there's no correlation. There's not anything really saying, hey, because of this, this tends to happen, right? It's not like up here where it looked like, as the grams of sugar were getting higher, the calories were starting to get higher. Down here, if we were talking sugar and calories, like let's make that comparison. So this down here is the sugar, these are the calories. Well, as I go up, so this was here, then I go more grams of sugar. This would have looked like it's going down, but then that point's going up, and that one's going up, and this is going down. So it's just kind of all over the place. So there's no real line or cluster that you can see to tell us whether it's positive or negative. So we would say no correlation for that one. So let's take a look at two graphs in example 2. So we're going to describe the relationship between the data and each scatter plot. So for A, it's age and vehicles owned. So we've got person's age in years, and then the number of vehicles that they've owned on the y-axis here. And as I look at the data, it's kind of like the one we were just talking about. It looks like they just threw dots on this paper. So we would say that there's no correlation for that one. So basically that means it doesn't matter if their age is increasing. It doesn't automatically mean that the number of vehicles that they've owned is going to increase. It might not, just depends on the person really. So just because they get older doesn't mean that they will have owned more vehicles in their lifetime. All right, so then we look at B, temperature and coat sales at a store. See how this is they're all kind of clustered together, looks kind of like a line. So we would say that there is a correlation. And if we kind of follow the data, follow that pattern that we're seeing, it kind of looks like from left to right, we're heading in a downwards direction here. So I would call this, excuse me, a negative correlation or negative linear correlation. Okay, so what we can gather from that negative correlation is that as the average temperature increases, it looks like the number of coats that they're selling decreases. So let's jot that over here. As the average temperature number of coats, oh my goodness, sold decreases. And we can kind of see that here. So it was at 35, we're up here at like 62-ish coats. And as that temperature is getting higher, the number of coats that they're selling is decreasing. In fact, look down here at 70 degrees, they were only selling maybe 12 coats at that point. Okay, so that's for this graph here. All right, example 3. We're going to get to that in just a second. So when the data shows positive or negative linear correlations, we can use what's called a line of fit, or sometimes it's called a trend line because you're looking for trends in the data. And we draw this line on the scatter plot as close to most of the data points as we can. So you kind of want to look at like putting it into the middle of the data. So here, I didn't do it perfectly, but I kind of drew like down the middle of these dots when I was looking at that. Oops, there it is. Down the middle of these dots. And so you kind of try to get a balance where you have like the same amount of dots above and below the line. So I was a little bit low on this. See how we've got like 3, 4, 5, 6, 7, 8 above here, but only like 3 down here. So I could have angled it a little bit differently to make it match this data a little bit better. But that's the idea. You're looking to put your line towards the middle of the data and then have equal amounts above and below whenever possible. So we kind of give you some instructions here basically to help you with your line of fit. So you basically, you have your scatter plot. decide whether it can be modeled by a line, because if it can't be modeled by a line, the line of fit doesn't make sense. And then we draw the line that appears closest to the data, like we were just talking about, and then we write an equation using two of the points that actually touch the line, so we can find that slope and we can find the equation of the line. And then just as a reminder, the points do not have to represent actual data pairs. So it doesn't have to be a piece of data from the scatter plot. It could just be two lines that happen to be on that fit line that you drew. Okay, so we'll kind of take a look at that in just a minute. So example 3 says, the table shows the total numbers Y in millions of subscribers to a video sharing website. X years since 2010. We're going to write an equation that models the total number of subscribers as a function of the number of years since 2010. And we're going to interpret the slope and the Y-intercept of our line of fit. So what we're looking at here, first of all, let's give our graph a title. So this would be our website subscribers, because these are all important details of a graph. So website subscribers. And then our x-axis is going to be our years since 2010. So this was years since 2010. So we won't think it's year one, it's 1 year after 2010, right? And then on the y-axis, it is the subscribers. And this one is talking about in millions. So we've got subscribers in millions. All right, so let's start by putting our data on the graph. So I have the point 0.9, so I have to kind of estimate that here, since these are counted by tens. 1 and 21, so over at 1, just above there, call that 21. 2 and 26, so 2, just above half, right? We'll go right there. 3 and 33, just under half. There we go, that sounds good. 4 and 43, that's also just under half. There we go. 5 and 53, oops, 53, a little higher, Mrs. Weber. 6 and 71, there we go, all the way up here. 7 and 76, so that one's just a little bit more than half. There we go. And 8 and 89, that one's almost to there. There we go. So if we're looking at our data, is it a perfect line? No. But is it in a line pattern? It is. So we would say that this has a linear correlation. And as we read left to right, it does look like it's going in an upwards direction. So a positive linear correlation. So we're going to draw. So we looked at, we made our scatter plot. We decided that it does have that line model. And now we're going to put our line of fit on there. So let's look to see about where we can put this. Let's see here. I get it right here. That's a little bit, let's kind of move up like that. Well, that one might work about right here. There we go. Positive. Let's draw our line in here. So let's see, I got 2, 3 above, and it looks like 3-ish below. Okay, let's try that. There we go. So not perfect, but it looks like I might have caught a data point here, maybe a data point there. I have 2, 3 above, and about 3 below here. So towards the middle of our data. Now, in order to figure out the slope of our line, we have to pick 2 points. So it looks like I caught the line right here at 76. I actually did get one of these data points right there already. And then it looks like I also kind of caught the line here. It's about 2 and 26. So we're going to use those 2 data points for this. So let's take those 2. Let's find our slope. So this was example 3. We have the points 2, 26 and 7, 76. So let's use those to find our slope. So we've got 76 minus 26 over 7 minus 2. If you like to use the table, remember that you can just draw your xy and then find the change on each side. So 76 minus 26 gives us 50. 7 minus 2 gives us 5. 50 divided by 5 is 10. So our slope for this line would be 10. So now we're going to use our slope and one of our points to do point slope form. So I've got, I think I'll use the 226 because they're smaller numbers. Doesn't really matter. You choose whichever one you want. So we got y minus 26 equals 10 times x minus 2. Let's do our distributive property here. 10x, 10 times 2 is negative 20 because we got that negative here. Bring all that down, y minus 26. Let's add 26 to both sides. And we've got y equals 10x plus negative 20 plus 6 is positive 6. So here's our equation that they were asking us for. And then it says, so we wrote our equation that models our number of subscribers. Now we have to interpret the slope and the y-intercept of the line of fit. So if we're looking at this, the y-intercept is 6. For this question right here, what it means is that in 2010, there were 6 million subscribers. Okay, so our y-intercept, we'll just abbreviate that, equals 6. So in 2010, because that was the 0 year, 6 million subscribers. And then if we look at our slope, right, that trend line slope that we found was 10. So the slope of 10, that means that the number of subscribers, oops, if I spell numbers correctly. Number of subscribers increased by 10 million each year. So remember, this is not exact. So this is more like an estimate because it was a line of fit. It wasn't saying, hey, every single year it absolutely goes up by 10 every time. But when we placed our line of fit, that line showed us that there is approximately 10 million new subscribers each year after 2010. So that's what that slope would mean for us. This is lesson 4.6a. In this lesson, we're going to talk about sequences and arithmetic sequences. So if we're looking at this, a sequence, something you've probably heard of before. It's an ordered list of numbers, and each number in a sequence is called a term. Each term, we're going to label it A sub n, and it has a specific position, which is what the n stands for in the sequence. So for example, if we're looking at this sequence here, 5, 10, 15, 20, 25, and then eventually A of n, which is like some random number in the sequence far down the way that we don't know yet, but maybe we could figure it out. But if we're looking at this, so 5 right here would be the first position, because it's that first number. 15 is like the third position. 10 is the second, 20 is the fourth, fifth. And then A of n is what we call the nth position. So it's some number in that sequence. And usually you can figure out, if you figure out the rule, you could say, oh, well, if I wanted to know the 100th term, then I could figure, okay, well, if it was, here's my rule for any number, and I could plug in 100 to figure out what that 100th term would be. But we're going to focus on arithmetic sequences. And with an arithmetic sequence, the difference between each pair of consecutive terms, so they come one right after the other, is the same. So the difference between those is the same. The difference is called a common difference, and that's a word that you're going to want to remember because you're going to use it quite a bit in this chapter or this lesson. Each term is found by adding the common difference to the previous term. For example, if I look at these numbers, 5, 10, 15, and 20, if I look from 5 to 10, well, I added 5. From 10 to 15, I added 5. From 15 to 20, I added 5. So I'm trying to figure out what am I adding to these numbers in order to figure out the change between them. So that plus 5 is the common difference. So we're going to look at example 1, and in example 1, we're given a sequence. It's telling us that it's an arithmetic sequence, and we're going to figure out what the next 3 terms are in this sequence. So I'm going to take these numbers, I'm actually going to put them into a table so I can kind of organize my thoughts with this. And these are going to be my terms, right? And then the position that they're in is going to be another row on my table. So example 1, we have position, and then we have our term. So let's kind of separate these into a table. So we have in the first position, -7. So position 1 is -7. Position 2 is -14. Oh my goodness. Started to write the negative up there when I should be writing the 2 up there. Position 2, -14. Position 3, we had -21. And position 4, we had -28. Now you notice we have these dots that follow. That just shows us that this sequence would continue on and on and on and on. So if I'm looking at this, I want to figure out what my common difference is. So from -7 to -14, I'm adding, oh wait, but it gets smaller. So I'm actually adding a negative number. So you'll often see it written as plus a negative, and then they put the negative in parentheses. Same thing from -14 to -21, adding -7. And -21 to -28, we're adding -7. So that common difference that we have for this one is -7. I'm going to label this CD for common difference, just to kind of shorten it up for us. So if I want to know the next 3 terms in my table, well, I have to do 5, 6, and 7. So those next 3 terms, position 5, 6, and 7. And, oops, forgot my parentheses here. Still going to be adding -7 each time. Or another way to think about it is subtracting 7. So -28 minus 7, or adding -7 will be -35. And then we'll have -42 and -49. So those next 3 terms that they were asking us about are -35, -42, and -49. All right, we also can graph arithmetic sequences. So down here it says to graph a sequence, we're going to let a term's position number n in the sequence be the x value. The term a of n is the corresponding y value. So then you kind of plot it as the point n comma a of n. So if you think about it, it's just like when we have our ordered pairs that are x comma y, but the position is the x and the term is the y. So if I were to look at this table up here, I'd have a point 1 comma -7 for that, 2 comma -14, etc. So when I'm looking at this, they give me a sequence here. So what I want to do, just like I did in the previous question, is I want to put it into a table to kind of sort my thoughts, especially since I need some ordered pairs to put on my graph. So I'm going to plot or make my table here. So I've got my position, which they refer to as n. And then we have our term, which we refer to as a sub n or a of n. So I have in position 1, I've got 4. Position 2, I have 8. Position 3 is 12. And position 4 is 16. So if we think about these as ordered pairs, remember this is kind of like our x and our y that we're used to seeing. So I have the point 1, 4 going on my graph. So over 1, up 4, put it up. I've got 2, 8, 3, 12, and 4, 16, all the way up here. So once we plot these, it asks, what do we notice? Well, I'm noticing that these dots are on a line. So we're noticing, we'll put it down here, points are on a line. Which is a really important thing to know as we continue in this, that these arithmetic sequences are going to create lines if we put them on a graph. Okay. All right, so for example 3, it says, does the graph, so this graph over here, represent an arithmetic sequence? And then we're going to give a little bit of an explanation to prove that. So as I look at this, first of all, I'm going to take these points that I have on my graph and I'm going to put them into the table that we're used to doing now. So for example 3, we have our position and our term. For position 1, we had 15, so 1, 15. Position 2, we have 12. Position 3 is 9. And position 4 is 6. So as we look at these, we're trying to figure out what is our common difference, because if it's going to be arithmetic sequence, we have to have common difference. So as I look at these, from 15 to 12, I notice I'm subtracting 3. From 12 to 9, I'm subtracting 3. And from 9 to 6, I'm also subtracting 3. So it looks like I am doing the same thing all here, and I'm adding this -3 every time. Or in other words, subtracting. So I noticed that the common difference, again, we'll label that CD, is -3. So because I have this common difference and it was making a straight line pattern, we can say that yes, this is an arithmetic sequence. Check for those common differences just to make sure that we've got our arithmetic sequence or not. This is lesson 4.6b. In lesson 4.6b, we're going to continue talking about arithmetic sequences. And we're going to be talking about some commonalities that we see among our sequences. So something that we know is that all arithmetic sequences have a constant rate of change, which is why they fall on a line. They make that straight line because they constantly go up and over by the same amount every time, that constant rate of change. So if we were to look at it in terms of the information that we have, so we have like a table of information. So if we have position, which we're going to refer to as n, and then we have our term, which we refer to as A of n, because we're going to use this information to see how to make an equation so that we can make our life a lot faster when we're talking about arithmetic sequences. So the position that we're talking about is n. The term is A of n. So it's kind of like subtext, so it's like lower down than this actual A is. And then here we have A and D. So we write it using those two things. So written with, that's just abbreviated for with, A and D, and you'll see how that works in just a few minutes. And then we've got our number. So if we look at the very first position, this is the term A of 1. So notice here was n, that was n. So we take the 1 that we plugged in here, put it in here, so that means it's our first term. If we were to write this as an expression, we would have A of 1, because there's nothing being added or subtracted, it's the first term. And let's just pretend that A of 1 is 4, just to kind of show it using numbers as well. So if I did my second position, I would have the term A of 2, and then I would take A of 1, which was our first number, plus D, which again is that common difference. So we've got plus D. And let's say that our first term again was 4, and let's use a common difference of 3. So we'd say plus 3, that would give us 7 for the number. So if we're looking at the pattern, we go 4 and then 7. So then if I did my third term, this is A of 3. I still use A of 1, but this time I have to do 2 sets of the common difference, right? Because I added 3 here to get the second one, then I had to add 3 again to get to the third term. So that would give us 4 plus 2 times 3. Well, 2 times 3 is 6, plus 4 gives us 10. So that's our next number in the sequence. And then as I continued down, I kept going with this pattern throughout, as long as I want to, I would end up at the position n, which is some random spot in the sequence that we're not sure of yet. But we could pick basically any number we wanted to replace n. So we would call that term A of n, because again, it's a number we haven't decided on yet. We would use A of 1, that very first term, plus, now notice, the number I multiplied times D here is 1 less than what our position was, right? Because it's taking into account how many times we've had to add the common difference. Because in that first one, we didn't have to add anything at all, because it was the first number. So I have, if I'm writing a generic format, I would have n minus 1, that's how I get the 2 right there, okay? The n was 3, minus 1 is giving me 2, times that common difference. So if I thought about it in terms of the numbers that I've been using up here, I would have 4 plus n minus 1 is still the same, because I haven't decided what number I'm using for n yet. Then we're multiplying by that common difference, which was 3. So this is a format that we can use all the time when we're looking at arithmetic sequences. So if we look right here, this is the formula that we were just creating. Notice how that looks familiar to what we were just looking at. So we have, it says let A of n be the nth term. Sorry, I'm going to highlight that first. Of an arithmetic sequence with the first term A of 1, common difference of D, and our nth term is given by using this. So if we use this formula, we could pick any number in the sequence and plug it in for n and be able to figure out exactly what number it would be in that sequence. So if I wanted the 25th term, I have A of 25, I would use that first number, which we had before was 4, plus 25 minus 1 times our common difference of 3. And I'd be able to figure out what the 25th term in the sequence is without having to make a table and continue on and on and on and on and on. So let's see what that looks like in terms of an actual sequence. So we have this, write the equation for the nth term of the arithmetic sequence, and then we're going to use that to find A of 16 for this question. So what we're going to look at here is we have, first we need to find our common difference. So let's use this purple for our common difference. So from 55 to 40, it looks like we're subtracting, right? So we're adding the negative number here. And if I'm subtracting this by 15. Same thing from 40 to 25 and from 25 to 10. So every time I subtract 15, I'm just going to write these two because I got a little smushed in there. So our common difference that we should make note of is minus 15. Let's slide this up a little bit. Example 1. We're going to write down, I'm going to abbreviate this like we've done before, and I'm going to use C.D for common difference. And that was negative 15 because we were subtracting 15 each time. According to the information that I have here, my first term in my sequence is 55. So that's my first term. So now I'm going to plug that information into my equation that I have, right there. So we have, let's write down our generic format first. So we have A of n equals A of 1 plus, in parentheses, n minus 1 times our common difference. So we know our common difference, we just used purple, so I'm going to highlight that. And on the chart, we substituted A of 1 I highlighted it with that pink color. So we're going to do that just for kind of keeping us on track with what we're doing. So they want us to use, or to find, the 16th term in this sequence. So A of 16, we're going to use that term to figure it out. So we've got A of 16 here, and that equals 55 was our first number, plus, now we were doing A of 16, so 16 was what is n, so we plug in 16 here, minus 1 times the common difference, which we know is negative 15. Now remember, since it's multiplication, we should put it in parentheses so we don't think that it's subtraction. All right, so remember, we always take care of our multiplication first. So we're going to multiply both sides here by negative 15. So I have a of 16 equals 55 plus negative 15 times 16 is negative 240. And 55 plus negative 240, can't do that part yet. I have to do negative 1 times negative 15, which is our positive 15. Okay, now we can add our 55 and negative 240, which gives us negative 185. Bring down that plus 15 because we haven't used it yet. So then we have a of 16 equals negative 185 plus 15, and we get negative 170. So the 16th term in the sequence is negative 170. Now, sometimes, and I forgot to do this part at the beginning, it asked us to write an equation for the nth term of our sequence. So what we can do, once we started this piece right here, we can actually simplify it just for n before we plug in the 16. So let's take a look at that over here. So we've got a of n equals a of 1 plus n minus 1 times d. So if they want this just in a generic format, and we're using this sequence, and we just want to have it in terms of n, they don't want us to plug in any numbers just yet, we would, in terms of like the 16th term, they don't want that, they just want a of n. We would have a of n equals, we do still need that 55, but for now, we're going to leave our n the way it is, because we're going to pretend we don't know what the term they want is yet. And then we have our d multiplied on the outside here. Oops, I forgot to put the 15. That number I wanted. My goodness. Sorry about that. All right, so here's our negative 15. So this is the number if we're going to multiply by both, just like we did when we actually plugged in 16. So we have a of n equals 55 plus negative 15 times n is negative 15n. Negative 15 times negative 1 is positive 15. So then I take a look at the common, the like terms. So we have 55, positive 15. So if I put those two things together, we've got a of n equals, I'm going to put that down here at the end as plus 70. And then we didn't use this minus 15n, so we're going to rewrite that. So this is kind of like if we were asked to graph, right? It looks very similar to our slope-intercept form. So it would be similar to having, let's write that, similar to our y equals negative 15x plus 70. So if they asked you to graph this function, we could put it in this slope-intercept format and graph it. And truthfully, if we have it simplified in this, it's a little bit shorter work when we go to add in these extra terms. So if I wanted the 16th term, I would just have to plug in 16, multiply, and add one time. It works either way, but if we want to know what it looks like in terms of just n, then I could simplify it like this. For example 2, it says online bidding for a geothermal heat pump increases by $25 for each bid after the $420 initial bid. Write a function that represents the arithmetic sequence, then graph the function. And then for part B, it says the winning bid is $1,520. How many bids were there? So what we're going to look at first, we have to write a function that represents the sequence. So we're going to take our format that we just worked with. Now, I'm going to use f of n for example 2 because it asks for a function. And we want to make sure that we're being true to our function notation. So for part A, we have f of n, which is a similar idea, right? This is a with the sub n. I still can plug in my number for n right here. It's just that different formatting, but it means the same thing. And so this equals still a of 1 plus n minus 1 times the d. All right, and we have, according to this, our initial bid of $420. So that is our starting value. So if it says it's an initial amount, something along those lines, it's your starting value. So we have $420 for the initial bid. That goes for a of 1 plus n minus 1. And then we have to look at the common difference. So according to this, it increases $25 for each bid. So that would be a common difference. Every single bid we have increases by $25. So that's our common difference. So we're going to multiply this by 25. And it's positive, but I still put it in parentheses to show the multiplication. So we're going to distribute this 25 to these two pieces here. 420 didn't get used. So we're just going to rewrite that. 25 times n is 25n. 25 times negative 1 is negative 25. Let's combine our like terms. So it's negative 25 and 420. So we have f of n equals 25n plus 395. So this is that function that we were looking for. And now we can use that function just like we've done in the past in order to graph our information. So just like when we have done this in the past, our initial bid, or not initial bid, our y-intercept is 395. So if I'm looking at my graph here, 395 isn't a perfect number on here. So I have to kind of estimate where I'm at with that. So 395 is almost 400. So right there. If we had one bid, so if we're looking at, you know, how we've done our values in the past, right? So we have our bid number and then the bid amount. We'll just abbreviate that with AMT. So for one bid, if I plug in 1 for n, f of 1 equals 25 times 1 plus 395. So f of 1 equals 25 plus 395, which is 420, which makes sense because that's what they told us is that first bid that they had. So 420 for that first bid. So we go down here to 1, our initial bid, $420. It's about halfway, well, a little bit closer to 425. So right there. If we looked at the second bid, we would have 2 times 25, which is 50 plus 395, and we would get 445. For 3 bids, if we plugged in 3, we'd have 25 times 3, which is 75, plus that 395 would be 470. Or if we did 4 bids, we would have 25 times 4, which is 100, plus that 395, so we got 495. So just to give us some more points on our graph here. So 2 and 445, so we got to kind of estimate it's almost to that 450. 3 and 470. So again, almost to that 475. And then 4 and 495. So that's almost to that 500. There we go. So there's our graph of our function. And then it says the winning bid is $1,520. And we want to know, well, how many bids were there in order to get to that winning bid? So what I'm going to do is take the $1,520. This is example, or part B for example 2. So we take that $1,520. Here's our equation. Let's rewrite that real quick. 25n plus 395. So the amount for $1,520 goes in for that f of n, because that's what it's equal to. That was that winning bid. Equals 25n plus 395. So basically what they're saying is, what's the winning bid? That means solve for n, right? So we subtract 395, just like we've done in previous lessons. That makes 0. Bring down the 25n. 1520 minus 395 is 1125. Divide both sides by 25. And we find out that n equals 45. So that means that there were 45 bids on this heat pump. I guess they're building it. But there were 45 bids before they got to the $1,520.